This is a recording of the lecture that I did today in class. Today is September 14th. It's over section 3.5 where we talk about work as an integral. In science, work refers to the force acting against a body that pushes the body or pulls it where the body is displaced. So a force acts on a body and the body actually moves from its initial position to a terminal position. This is a constant force acting on a body. Now, if I stand up against a wall and push with all my strength, and the wall doesn't even move, even though I'm applying a force, no work is done because there's been no displacement. In general, if work is done by a constant force, then work is the product of force and the distance that the object is moved. So this is for a constant force. Force doesn't change throughout the action. For instance, if I pick up a 20-pound bag of potatoes and put it up on a table that's 4 feet high, then the work is the product of the 20 pounds times the distance, 4 feet, for a total amount of work of 80 foot-pounds of work. So those are examples of work units in the U.S. system. We measure force in pounds, distance in feet, and so work is in foot-pounds. In the international system, you'll often see force is done in newtons and distance in meters. And then Newton meters would be called joules. I wrote down newtons. Let me fix that. This should be joules of work. If we have something small that we're moving, like a spring is typically measured, where the force is in dynes, the distance is in centimeters, then here are my favorite units of work. Ergs, E-R-G-S, ergs of work. Dynes times centimeters is ergs. If force is not constant, if force varies over the interval, maybe forces, for instance, we're pushing something up a ramp. It takes a lot more force to get it going from a stop position, but then as it goes up the ramp, there's more force required to continue to push it. So force varies based upon where it is on its path. If the force varies based upon its location on a number line in X, then what we do is we take that interval from A to B and we subdivide it into an infinite number of subintervals till we get out here to the kth subinterval, and make this subinterval so small that over that interval force is essentially constant, and so that the work done on the kth subinterval is the product of the force. Use either the right endpoint or the left endpoint to determine the force. It won't matter because that interval is going to be so small, times the distance that it travels over that interval. And we do that over each subinterval so that when we form this Riemann sum where I add up little pieces of force on little tiny intervals from k is equal to 1 to n, and let n go to infinity so that the delta xk's go to 0, then we recognize that Riemann sum as giving us a definite integral. From A to B, the force now is a function of x, and the delta xk becomes our increment in x. So we cut our interval up into tiny pieces, add up the force as constants on the tiny pieces, and then we can get a definite integral that computes the work done. So work is the integral of the force integrated with respect to x. So in my first example, suppose we're moving an object down a number line, and what I've written here is that the force is inversely proportional to the square of the distance that that object is from the origin. In other words, force is 1 over x squared. That many pounds is required to move the object on this number line, and we want to compute the total amount of work done in moving the object from its location 4 feet from the number line, 4 feet from the origin, to 16 feet from the origin. So here's our number line, there's the origin. We're going from 4 to 16 by applying this force, which varies according to where we are on this x-axis. So what I said above was that work is simply the integral from a to b of the force as a function of x integrated over the distance dx. Our distance is going from x is 4 to x is 16, so we're integrating 1 over x squared. We rewrite that as x to the negative 2, then add 1 to the power, divide by the new power, and so we get a negative 1, x to the negative 1, which I'll write as 1 over x. And so we have negative 1 over 16 minus a negative 1 over 4. So that's 1/16, negative 1/16 plus 4/16 gives us 3/16. I've got pounds and feet, so I've got foot-pounds of work. We cut things up into tiny pieces to get the integral to compute the work force if force depends on position. Here's another example. I've got a cable 50 meters long, and it has a density of 3 kilograms per meter. The cable's hanging from the winch. How much work is done in winding it up? So let me kind of diagram that. Here's our cable. Here's the winch that it's hanging from. This total length is 50 meters, and it weighs 3 kilograms per meter. Now imagine this thing getting rolled up here so that this length becomes less and less and less. As this gets less and less and less, the amount of force needed to apply changes because there's less weight hanging there. So I've got a variable force acting on this. And what we'll do is we'll cut this up into a tiny interval. Say we'll just look at a slice of this cable. Let's call this the x-axis. And so a delta x meter slice of cable. And let's measure how far it has to go to get from where it is on this x-axis to where it needs to be. So let's say that this is x is 0. This up here is x is 50. And this is just some random x in between that. So the distance that it has to travel is 50 minus x meters. The weight of that small slice of cable is going to be its force in kilograms. So I take my 3 kilograms per meter and I multiply it by delta x meters, and you can see that the meters will cancel, and so we have 3 delta x kilograms of force on that slice. So that the work done on that slice, that's what we call delta W, was just going to be the force, our 3 delta x kilograms, multiplied with our distance, 50 minus x meters. And so our work units would be kilogram meters. Back there we said that measurement is joules. This becomes a definite integral. The total work is the definite integral of my 3 times my delta x, which becomes the dx in the integral, times the distance, force times the distance. And we're going to make these cuts of cable all along its total length from x is 0 to x is 50. So the idea gives us a very simple integral, finish it. I'll pull out the 3, integrate 50 and get 50x, integrate x and get x squared over 2, and we evaluate this from 0 to 50. 50 times 50 is 2,500. 50 squared is also 2,500. Then we multiply that by 3. The 0 gives us 0. 1 2,500 minus a half 2,500 is 2,500 over 2, so we get 7,500 over 2 once I distribute the 3. I said these were kilogram meters, which are called joules of work. Okay, I've got another example for you. Now we're going to talk about the work done in stretching or compressing a spring. Every spring has a natural length, and Hooke's law states that the force needed to either stretch that spring or compress that spring x units beyond its natural length is directly proportional to that distance that it's being stretched or compressed, which says that force is directly proportional to the distance. K is the constant of proportionality. It's unique to each spring. It'll be called the spring constant. We can discover what the value of the spring constant is, and then we can compute the work done in stretching this spring is just force times distance. So with Hooke's law, it's kx times dx. And we take natural length at being 0 and distance beyond its natural length to be number b. Or if I'm going from a certain level beyond its natural length, then I can say that I'm going from A to B, where natural length corresponds to the origin and distance beyond its natural length. So there's the natural length, and then we're going to take it from A units beyond its natural length to B units beyond its natural length. That's the stretching amount. So work is equal to K times X dx. So in our spring problems, we look for an ordered pair that'll help us to find K. Then once we find K, we set up this easy integral, integrate it, you get kx squared over 2 from whatever to whatever. Okay, so let's look at the next example. We're told it takes a force of 3 pounds to stretch a spring 1/4 from its natural length. Okay, so we've got 3 pounds of force if the distance stretched is 1/4 of a foot. So before we can find work done, we find the spring constant. We know that F is K times X. We've got the force, and we've got the distance. And so if you multiply both sides by 4, you get 12 is equal to the spring constant. Now we can find the work done. The work is the integral of K times X dx. So we've got the integral of 12 times X dx, and we're going to go 6 inches beyond its natural length. So we're going from natural length to 1/2 foot. From natural length to 1/2 foot. Make sure your units agree, foot pounds. Okay, so we integrate. 12x integrated gives us 6x squared from 0 to 1/2. 1/2 squared is 1/4, 6/4, or 3/2 foot-pounds of work to do this stretching. Okay. Now pay attention to what you're given. Here we were given a force and a distance and asked to find the work. In my next example, we're given an amount of work to stretch a spring, and we're going to use that to find work. So if I'm given work, then I begin with this. Work is the integral of k times x dx. I'll put my 4 ergs of work here, and we're going from its natural length to 10 centimeters beyond its natural length. And so we're going to take this equation and solve it for k. So I have 4 is equal to kx squared over 2 from 0 to 10. 10 squared is 100, divided by 2 is 50. So I have 4 is equal to 50k. So 4 over 50, or 2 over 25, is k. Now we can use that to answer the question, because now we know force is equal to 2 over 25 times x. We want to go 4 centimeters further. So that's from the 10 centimeters beyond its natural length to 14 centimeters beyond its natural length. So our work integral, we're starting at the 10 centimeters beyond its natural length and going to 14 centimeters beyond its natural length. And then we have our force times our distance. So when we integrate that, we get an x squared over 2. The 2 cancels with that 2, so I have 1 over 25 times x squared from 10 to 14. So 1 over 25, 14 squared minus 10 squared. These are in ergs again because I have centimeters and my force is in dynes, so I get to use ergs of work. The next type of work integral that we're going to do is work done in pumping liquid from a tank. So to determine the work done in pumping this water out of the tank, imagine taking slices of the water of some thickness, right? Delta X, delta Y. The slices take on some sort of shape depending on the tank. If we know the density of this liquid in pounds per cubic feet and multiply by the volume of that particular slice in cubic feet, then we can get the number of pounds to move that slice. Then we move it one slice at a time, and we can set up an integral that does this to us over for the entire depth of the water. We'll be needing the weight density of the water or the liquid. If it's in pounds per cubic feet, then our weight density already has the gravitational constant in it. If we're in metric units, often you'll not have the gravitational constant part. In metric units, you'll be given the mass density. So if you're given the weight density, then that's typically denoted by the letter delta, and it includes the gravitational constant, includes the force of gravity. But if you're told you're given mass density, that's the weight per unit area, then the mass density will need to be multiplied by the force of gravity. So in international units, the gravitational constant is, 9 point, oh gosh, what is the gravitational constant? Let me look that up. 9 point something something, 9.6, 9.2. Geez, I don't know. I'll just hope that we're doing everything in our English units for our examples, and we'll look up the weight density. So let's not worry about that. We'll have ours with the gravitational constant in it. If we need to put it in there in web work, we can look it up. Okay, so here's my first example. A cylindrical tank, that means it looks like a can, of diameter 4 feet and height 6 feet is half full of water, weighing 62.4 pounds per cubic feet. Find the work done in emptying the water to the top of the tank. So here's what we got. We've got this tank shaped like a can. We got the dimensions of this tank. It is 4 feet in diameter. It is 6 feet tall, and it's half full of water. So it has water to 2 feet. Find the work done in emptying the water to the top of the tank. So here's how we're going to do it. We're going to put an axis smack dab through the center of the tank. Let's put the origin right here and bring this up here so that this point is the ordered pair 0, 6. And if my diameter is 4 feet, then the radius here is 2 feet. So this ordered pair would be 2, 6. And here's the origin. Okay, so we've got water up to a level of 0, 3 or 2 feet deep. Oops, sorry, I don't know where this 2 feet came. Half full of water, so this should be 3 feet. Okay, so this point is 0, 3. Okay, now we've got this liquid and we're going to cut it up in an infinite number of slices. So an example of a slice is this. And if I pull that out, it looks just like a circular disc, whose radius is the same as the radius of the tank, and whose thickness is delta. If that's the y-axis, then I would denote my thickness is delta y. To get the force on this kth slice, we take the weight density, 62.4 pounds per cubic feet, and we multiply it by cubic feet. Now, what's measured in cubic feet? The answer is, it's the volume of the slice. So we need the volume of our slice, which will be in units of cubic feet. Then the cubic feet will cancel, and you see how we're left with our force units of pounds. Now our slice is a disc whose radius, no matter where it's put, the radius of this slice is going to be 2 feet. And so the volume of the slice is pi times 2 squared times its thickness. And then we've got the 62.4, and that's the force on the kth slice. Actually, will be on the k slice. That's my y-axis. So let's just call it the force on the slice. Now we have to see where that slice has to move. I put it at some arbitrary y coordinate on here, and I have to take it to a y coordinate of y is 6. So my claim is that the distance the slice has to move is 6 minus y. And now our work becomes an integral of the force times its distance. So we built the force by taking the weight density times the volume of the slice. The delta y becomes the dy, and then the distance. And then the integral sign represents the depth of the liquid, because we make these slices only in the liquid. We're halfway full, so the liquid goes from 0 to 3. Okay, it's a trivial integral to compute. This is a constant, it comes out. So we have 62.4 pi, 2 squared is 4, integrate 6 and you get 6y. Then you have a y squared over 2, evaluated from 0 to 3. I'm in pounds and feet, so these will be foot-pounds. I'll save you the boring part of plugging the number in. So that's the idea. The shape of the tank is going to determine what our slice looks like. And so we'll have to figure out what a slab of that slice looks like and apply a volume formula to it. Area of the base times the thickness. So in the next one, we're told that a vat is a triangular prism, 3 feet high, 6 feet long, 4 feet wide. So that means the opposite faces are triangles, like that. And then we've got another one out here somewhere. And then we've got prism going something like that. Okay, we're told it's 3 feet high, 6 feet long, so from here to here is our 6 feet, and 4 feet wide, that's from here to here. Contains water to a depth of 2 feet, and we're going to pump the water to the top of the tank. Okay, so I'm not interested in the depth, I'm interested in the face. The face is what's going to determine the shape of the slice. So let's take our coordinate system here and put this triangular face right here with the vertex at the origin. Then imagine it going back into the paper 6 feet and the other face on the opposite side. We are told it's 3 feet high, so this ordered pair would be 0, 3. It's 4 feet wide, so each side of these is 2, that's the x direction, and there's 0, 0. Okay, it's filled to a depth of 2 feet, so let's put that here. That's the order pair 0, 2. And now we're going to take a slice of this liquid at some arbitrary y value of thickness delta y. Okay, now imagine pulling that slice out. You're pulling it out from the entire vat. So we're pulling this slice out here, and if I pull that out, you should see that a slice looks like a rectangular slab. We need to know the shape of the slice because we're going to take its volume, multiply it by our 62.4 pounds per cubic feet of water weight density, and to get the total number of pounds. To get this volume of rectangular slab, we'll need to compute this length, then how far back it goes, that'll be the 6 feet, and then the thickness of delta y. So the volume is going to be the length times 6 times delta y. Now, I want to get length in terms of y, and it depends on where I place the slab along this line. So if I can write the equation of this line, then I can figure out what the length is. It's whatever this x-coordinate is, done twice by symmetry. So let's get the slope of this line. We've got a change in y of 3 and a change in x of 2, and it goes through the origin, so this is the line y is equal to 3/2 x. But the length is 2 times x, so let's figure out what x is. Take this equation and write x in terms of y. And now put that in here. We got the length is 2 times 2/3 y. To get both of these, right graph minus left graph. Okay, so our length is 4/3 y. Our width is 6, and our thickness is delta y. Now we need distance. It's placed here at some random y coordinate, and we need to pump it to a height of 3. So like before, this height, the distance that it moves, is 3 minus y feet. Volume is in cubic feet, distance is in, the weight density is in pounds per cubic feet, so our force is 62.4 pounds per cubic feet multiplied with our volume, 4/3 y times 6 times delta y cubic feet. And that gives us our force in units of pounds. The distance is our 3 minus y feet. And now we get the total work done by summing that up. Force move the dy out here, and then the 3 minus y. The integral sign represents the depth of the liquid. These slices are made from a depth of 0 up to a depth of 2. Okay, so to do this work integral, we multiply 62.4 with 4/3 and 6, pull it out here. Then we integrate the y times 3 minus y, so 3y minus y squared, from 0 to 2. So 62.4, 4 times 6 is 24. 24 divided by 3 is, I don't know, 8. Then we have 3y squared over 2 minus y cubed over 3 from 0 to 2. Whatever number that is, again, our units will be foot-pounds. Okay, let me get you another one here to show you how the shape of the tank helps us to determine the force by influencing the volume of the slice. In this example, a tank is a sphere, so it's shaped like a basketball. Radius is 3 feet, and it's full of milk, weighing 64.5 pounds per cubic feet. We're going to pump the milk through a pipe that is 1 foot tall at the top of the tank. Okay, so the 1 foot tall is going to affect the distance that the slice travels. It doesn't affect the shape of the slice. We're going to assume that the pipe is dimensionless. Maybe keeps the same shape as the slice coming out. I don't need the three-dimensional aspect of it. I do need to imagine what a slice looks like. So I'm going to take this sphere and picture it as a circle and put it on a coordinate system. The easiest circle that I can write the equation of is a circle centered at the origin. So I'm going to place that circle with its center at the origin. Circle centered at the origin of radius 3 has equation x squared plus y squared is 3 squared. And now I'm going to fill it full of liquid from a height of y is equal to negative 3 up to a height of 3, and then we're going to pump it to a height of 4. Now you picture this as a sphere, and we're going to make a slice in there at some arbitrary y value. So a slice will look like this. But when I pull it out, it takes the shape of the container. So a slice is going to be a circular disc. We'll find the volume of that slice in cubic feet, multiply it by pounds per cubic feet, and we'll get force. The radius of that slice is going to depend on where this is placed. It's whatever this x-coordinate is on the circle. If I place it there, the radius is different than if I place it here or here. So we're going to figure out the radius based upon whatever x is on the circle. So let's take this equation and solve it for x. We get that x squared is 3 minus y squared, so x anywhere on this circle, I'm sorry, not 3, we want 9. And I'll take the positive square root because I can take my radius to be a positive number. And then the volume of the slice will be pi times that radius squared times the thickness, which is a delta y. So we'll have pi times the square root of 9 minus y squared times delta y. And so the force, right, this is in cubic feet, so the force will be that times 64.5. Now the distance that has to travel is from where it is at some arbitrary y-coordinate to a height of 4. So I take the top y minus the bottom y. 4 minus y is the distance. Now if y is below the x-axis, it'll be a negative number. And 4 minus a negative number will make that distance bigger than 4. So it makes sense. Now we multiply force times distance and put it in an integral. And we get our work integral. Golly, what a strange looking W. Let's try that again. We get our work integral to be our force, 64.5 pi radius squared 4 minus y dy. Now the integral sign reflects the depth of the liquid that we're slicing up, and we're slicing it up from a depth of minus 3 to 3 on the y-axis. Okay? So to do this integral, we'll square this. We'll lose the square root sign, so we'll have a 9 minus y squared. You'll have to FOIL it out with the 4 minus y. Pull out the constant, and then integrate term by term. So I'll leave that part up to you. So that reminds me of the distance in a previous example. We had a second part. When pumping the water out of this tank, nothing changes whether I'm pumping it to the top or a certain distance above the top in terms of the volume of the slice. The only thing that changes when you pump it above the top of the tank is this. Distance changes if we pump to a height 2 feet above the top of the tank. Because now I'm pumping it from a height of 6 up to a height of 0.8. So if I'm going 2 feet to the top of the tank, everything stays the same, but this piece right here becomes 8 minus y. The depth of the liquid stays the same. The volume of the slice stays the same. The only thing that changes is the distance that the slice travels. So if you can remember that you find your work by finding the shape of the slice, then you find the volume of the slice based upon its shape. It might be constant, it might change depending on the shape. Multiply it by the density of the liquid. All of that will give you the force. Then you multiply that by the distance that it travels. Then that will be in feet. This will be in pounds. And then you compute the total work, where the numbers here represent the depth of the liquid. Okay? If your units are going to be in metric units, then you probably have to multiply by the gravitational constant. All right, that's it for this section. We'll do some more examples next time.